All right, let's dive right into one of the biggest, most mind-bending questions we can ask. What is our reality actually made of? I mean, think about it for a second. Is it possible that everything you see, everything you are, is at its core just information? Like we're living inside some kind of cosmic computer program running on ones and zeros. It's a really powerful idea for sure, but the question is, does it actually explain the universe we see around us? Let's find out. So, here's our game plan. First, we're going to look at why that simple idea of reality as information kind of falls apart. Then we'll dive headfirst into the seriously strange quantum world. We'll get to know the rules of its fundamental particle, the qubit, figure out how we measure all its weird uncertainty, and then finally see what all this means for the future of, well, everything. Okay, first up, is reality just information? We're about to push up against the limits of this whole digital dream idea. This quote really gets to the heart of the problem. The idea that reality is just simple bits, ones and zeros. It has descriptive power. It can describe what something looks like, but it has absolutely no explanatory power. It can't tell us why things are the way they are. And here's why that is. A classical bit, a 1 or a 0, is totally passive. It just sits there. Bits don't have any built-in machinery to do anything or interact with each other. They need an outside computer to read them, to interpret them, to give them any meaning at all. They can describe the shape of a cloud perfectly, but they can't explain the laws of physics that made that cloud form and move in the first place. So think of it with this framework. Mathematics is for describing things. It's the language of shapes and relationships, and that's where classical information theory lives. But physics is what explains the actual machinery behind reality. It's the why. So if we want an explanation, not just a description, we have to go deeper than pure math. We have to get into the physics of it all. Okay, so if classical bits just don't cut it, we have to peel back a layer. And that brings us to the quantum realm, where we find the real and, let me tell you, very, very strange rules of the game. And these rules are just bizarre. At this fundamental level, reality isn't solid or predictable at all. It's run by concepts like superposition, where a particle can be in many states at once, and entanglement, where two particles can be linked across the entire universe instantly. This isn't just a description anymore. This is the actual operating system of reality. So, if the game has completely different rules, then the basic piece of information has to be different too. It's time to meet the hero of our story, the qubit. And believe me, this is not your average bit. Right? A classical bit is simple. It's either a 0 or a 1. End of story. But a qubit, the fundamental unit of quantum information, can be a 0, it can be a 1, or it can be a mind-bending combination of both at the exact same time. It's just pure potential floating in a cloud of probability until the moment you look at it. But all of this strange power comes with some equally strange rules about what you can't do. These are the no-go theorems. The first one is the no-cloning theorem. Think about how many times a day you copy and paste something. Well, you can't do that with an unknown quantum state. The very act of measuring it to get the information to copy it destroys the original state. It's not just a bug, it's a feature. This is actually the foundation for things like totally unhackable communication. And it doesn't stop there. Next up, we have the no-deleting theorem. Just like you can't perfectly copy a qubit, you can't just drag one to the trash can and empty it. It's impossible. This points to a really deep conservation of information at the most fundamental level of reality. Information, it seems, just can't be destroyed. And finally, there's the no-broadcast theorem. You can't send one unknown qubit to two different people at the same time. You can't CC anyone on a quantum email. Quantum information is inherently private, a one-to-one kind of deal, which, again, is another reason it's so incredibly secure. Okay, so if these qubits live in this fuzzy, uncertain world of maybe, how in the world do you measure that? How do you put a number on how mixed up a quantum state is? Well, the tool for the job is called von Neumann entropy. The simple way to think about it is that it's an uncertainty meter. It's a way to measure how much we don't know about a quantum system. It puts a hard number on the amount of mixedness in any given state. And this whole idea gets way clearer when you compare a pure state to a mixed state. A pure state is when we know everything there is to know. It's a coin that has landed, and you can see its heads. Complete certainty. So its von Neumann entropy is 0. A mixed state, on the other hand, is the coin that's still spinning in the air. It's a jumble of possibilities, 50-50, heads or tails. It's full of uncertainty, so its entropy is greater than 0. And you can see that perfectly right here. On the left, a pure state. We have 0 uncertainty, so the entropy bar is at 0. But on the right, you have a maximally mixed state, a situation where things are as uncertain as they can possibly be. And that entropy bar shoots right up. The more mixed up things are, the higher the bar goes. So we've gone through some really weird rules and a whole new kind of information, but why does any of this matter? Well, it matters because understanding this stuff is the absolute key to the future of computing, a future where we stop building computers on top of reality and start computing with the fabric of reality itself. Now, harnessing this power is, and I can't stress this enough, incredibly hard. Quantum states are unbelievably fragile. The tiniest vibration, the slightest change in temperature, what physicists call decoherence, can just wreck the whole calculation. That's why quantum error correction is so critical. And even if you protect it from all that, the very act of measuring your answer at the end collapses all of that beautiful quantum potential into one single, boring, classical answer. And all of this brings us to what might be the most profound idea of all. Maybe we've had this whole thing backwards. Maybe we're not just building quantum computers inside our universe. Maybe reality, from our point of view, is a complex quantum computer. Which leaves us with this final, gigantic question. If our universe is a quantum computer running on the fundamental laws of physics, what is the calculation? What problem is it solving? And what is the ultimate output of reality itself supposed to be? It's a thought that kind of changes how you look at, well, everything. Thanks for diving deep with us.